Section: Introduction. In this section, we explore functional differential equations, FDEs, which are important in various research fields. FDEs are a type of partial differential equation that involves functional derivatives, where a functional takes an input function and maps it to a real number. We define a functional derivative as the derivative of a functional with respect to the input function at a specific point. FDEs are crucial in areas like Fokker-Planck systems, turbulence theory, and quantum field theory, among others. We note that while FDEs are widely applicable, analyzing them numerically can be quite complex. Over the years, several numerical approximation methods have been developed, such as functional power series expansion and finite difference methods. However, these methods often oversimplify the solutions to reduce computational costs. For example, the functional power series expansion is only valid for input functions near the expansion center and lacks general convergence guarantees. Similarly, the Reynolds number expansion is limited to cases where the Reynolds number is close to zero, which is not practical for turbulent flows. To tackle the challenges of computational complexity and limited approximation capabilities, we propose a hybrid approach that combines physics-informed neural networks, PINNs, with the cylindrical approximation. In the first stage, we expand the input function using orthonormal basis functions, transforming the FDE into a high-dimensional PDE based on the expansion coefficients. We demonstrate that the approximated functional derivatives and FDE solutions converge, confirming the reliability of our cylindrical approximation. In the second stage, we solve the resulting high-dimensional PDE using a PIN, which is effective for solving such equations without a mesh. Our method significantly reduces computational complexity compared to traditional discretization methods, requiring only a polynomial order of the input functions and functional derivatives. This is a substantial improvement over existing methods, allowing us to represent a broader class of input functions and functional derivatives. As a proof of concept, we conduct experiments on two FDEs, the functional transport equation and the Burgers-Hoff equation. Our results indicate that our model accurately approximates both the solutions and their functional derivatives, achieving a typical relative error of around 1,000th. In summary, our contributions are threefold. We introduce a novel learning scheme for FDEs that effectively addresses computational complexity. We prove the convergence of our approximations, and we demonstrate through experiments that our model can accurately capture FDE solutions and their derivatives. Section Summary. In this section, we introduce functional differential equations, FDEs, which are complex equations involving functional derivatives and have applications in various fields. We propose a novel hybrid approach that combines physics-informed neural networks, PINNs, with a cylindrical approximation to significantly reduce computational complexity and extend the range of input functions and functional derivatives that can be accurately represented, demonstrating its effectiveness through experiments on specific FDEs. Section: Related work. In this section, we discuss related work on functional differential equations, FDEs, which are widely studied in various research areas. Most research has concentrated on the theoretical aspects and formal solutions of FDEs, with limited numerical algorithms available for general cases. We note that a numerical method has been proposed specifically for the Hamilton-Jacobi functional equation in optimal control problems, utilizing spacetime discretization. Another approach also employs spacetime discretization with tensor decomposition. We highlight the carbon monophosphide ALS algorithm, which combines cylindrical approximation with finite difference methods and tensor decomposition, requiring a computational complexity of order m raised to the sixth power. In contrast, our model only requires a complexity of order m raised to the power of r, where r is typically 1 or 2 for most FDEs. Additionally, our model is mesh-free, eliminating the need for discretization. The cylindrical approximation we use is based on stochastic process theory and serves as a generalization for FDEs, similar to the spectral method for partial differential equations, PDEs. Recent papers summarize the convergence theorems related to this approximation, which differ from those in previous works tailored for practical applications. We provide further technical details and comparisons in the appendix. Next, we outline our proposed approach, starting with the cylindrical approximation. We introduce this approximation for functionals, functional derivatives, and FDEs, transforming FDEs into high-dimensional PDEs. We also establish convergence theorems for this approximation, with a detailed mathematical background available in the appendix. We define the cylindrical approximation of functionals, where any function in a real separable Hilbert space can be uniquely represented using an orthonormal basis. By substituting this representation into a functional, we create a multivariable function. Truncating the series at a certain point gives us the cylindrical approximation of functionals, with a projection operator defined accordingly. We then define the cylindrical approximation of functional derivatives. The functional derivative is expressed in a way that is more practical for computation, allowing us to represent it as an orthonormal basis expansion. We note that the coefficients of this expansion relate to the partial derivatives of the multivariable function we defined earlier. Our first main theoretical contribution is a convergence theorem for the approximated functional derivatives, which states that as we increase the truncation point, the approximation converges to the actual functional derivative. We also discuss the convergence rate and provide a technical discussion in the appendix. Finally, we define the cylindrical approximation of FDEs, focusing on an abstract evolution equation that represents a significant class of FDEs relevant in various fields. We present the cylindrical approximation for this equation and establish a second main theoretical contribution regarding the convergence of solutions. Under certain conditions, the solution of the approximated equation converges to the solution of the original equation as we increase the truncation point. We conclude by applying the cylindrical approximation to two specific FDEs, the functional transport equation and the Burgers-Hoff equation. Section Summary. In this section, we review existing research on functional differential equations, FDEs, highlighting the limited numerical algorithms available and introducing our cylindrical approximation method, which simplifies the computation of FDEs without requiring discretization. We also present convergence theorems for our approach, demonstrating that our method effectively approximates solutions to various FDEs, including the functional transport equation and the Burgers-Hoff equation. Section. Application 1. Functional transport equation. In this section, we first develop a straightforward functional differential equation, known as the functional transport equation, FTE, which extends the concept of the transport equation, or continuity equation. The FTE is defined with the initial condition that at time 0, the function f of theta equals f_0 of theta, where theta is within the range from -1 to 1, and u of x is a specified function. Specifically, we set the initial condition as f of theta at time 0 equal to a constant ρ_0 multiplied by the integral of u of x times theta of x. The exact solution for f at time t is given by f_0 of theta minus u times t, which we can derive by substituting into the equation. We provide further details and motivations for the FTE in the appendix. Next, we consider the cylindrical approximation of the FTE, which has the initial condition f of a at time 0 equal to f_0 of a, where theta of x is expressed as a sum of coefficients a_k multiplied by the basis functions phi_k of x. The initial function f_0 of a is defined in terms of f_0 of the projection of theta, resulting in a sum involving the coefficients a_k and the constants u_k, which are calculated using the inner product of u and phi_k. We utilize Legendre polynomials as our orthonormal basis. The exact solution for f at time t is then a sum involving ρ_0 and the coefficients a_k adjusted by the constants u_k and time t. In our experiments, we explore two types of FTEs, one where u_k is a constant for k equal to 1 and 0 otherwise, and another where u_k is a constant for k less than or equal to 14 and 0 otherwise. We refer to these as the linear and nonlinear initial conditions, respectively. We solve the resulting high-dimensional partial differential equation using physics-informed neural networks, PINNs. Moving on to our second functional differential equation, we examine the Burgers-Hoff equation, BHE, which is significant in turbulence theory. The initial condition for the BHE is similar, with f of theta at time 0 equal to f_0 of theta, where theta is defined over the interval from -1/2 to 1/2. We specifically use a Gaussian initial condition for f_0 of theta, which involves a constant and an integral that includes the covariance matrix C. The exact solution for f at time t is expressed in terms of a transformation involving theta and an integral that accounts for the Gaussian distribution. We note that our equation is a modified version of the original BHE, where we make it dimensionless and ignore the advection term. More technical details can be found in the appendix. The cylindrical approximation of the BHE also has an initial condition f of a at time 0 equal to f_0 of a, with theta expressed as a sum similar to the FTE case. The initial function f_0 of a incorporates the covariance matrix, which we compute using integrals involving the basis functions. For our experiments, we consider two types of covariance matrices, one where the covariance is a constant for all indices and 0 otherwise, and another where the covariance is a constant only for the first index. We refer to these as the delta and constant initial conditions, respectively. Again, we solve the resulting high-dimensional PDE using PINNs. Section Summary. In this section, we construct the functional transport equation, FTE, as a generalization of the transport equation, providing its exact solution and exploring two types of initial conditions. We also introduce the Burgers-Hoff equation, BHE, detailing its modification and exact solution, while applying different covariance matrices to derive initial conditions, all of which are solved using physics-informed neural networks, PINNs. Section. Step 2. Solving approximated FDEs with pins. In this section, we introduce the process of solving approximated fractional differential equations, FDEs, using physics-informed neural networks, PINNs. PINNs are powerful tools that can approximate solutions to partial differential equations, PDEs. We consider a PDE where the change in a function over time is related to some operator acting on that function, along with an initial condition that specifies the function's value at the start. The variables we focus on are time and space, which we randomly sample from specified intervals. To compute the solution, we input these variables into the pin, which processes them through layers and activation functions. The output we seek is an approximation of the function. We define a loss function that combines the difference between the predicted and actual values, as well as the boundary conditions. We calculate the necessary derivatives using automatic differentiation and minimize the loss through backpropagation. Next, we apply this method to high-dimensional PDEs, using specific inputs and outputs related to our FDE with a linear initial condition. We again compute the necessary derivatives and losses, which we minimize using mini-batch optimization. We also discuss the computational complexity of our approach, which is significantly lower than traditional methods. Our method scales better with the size of the input functions and allows for a broader range of polynomial or Fourier series approximations. The choice of basis functions is crucial for efficiency and depends on various factors related to the specific FDE. In summary, we transform an FDE into a high-dimensional PDE using cylindrical approximation and solve it with a pin, which acts as a universal approximator. Our model is compatible with existing techniques in the pin community, enhancing its versatility. Section Summary. In this section, we introduce the use of physics-informed neural networks, PINNs, to solve approximated functional differential equations, FDEs, by treating them as high-dimensional partial differential equations, PDEs. We highlight that our approach significantly reduces computational complexity compared to traditional methods, allowing for a broader range of input functions and functional derivatives to be represented effectively. Section. Experiment. In this section, we numerically solve the functional transport equation, FTE, and the boundary heat equation, BHE, to demonstrate our approach. These equations are suitable for our experiments because we have their analytic solutions, which help us calculate absolute and relative errors, key metrics in analyzing partial differential equations, PDEs, and functional differential equations, FDEs. It's important to note that most FDEs lack known analytic solutions due to their complexity. For our setups, we utilize a 4-layer physics-informed neural network, PIN, that combines 3 types of layers: linear, sign activation, and layer normalization, followed by a final linear layer. Our total loss function is based on the smooth L1 loss, which is the sum of L1 and L infinity losses, and we apply softmax loss reweighting. We use the Atom W optimizer and a learning rate scheduler that features a linear warm-up followed by cosine annealing. For sampling, we implement Latin hypercube sampling for our training, validation, and test sets. In the case of the BHE, we adjust the sampling range quadratically to stabilize training. We measure performance using L1 relative and absolute errors, which are standard metrics for numerical analysis. We prefer absolute error when the analytic solution is close to 0, as relative error can become misleading in such cases. We set specific parameters. The initial values for certain variables are all set to 1, with one variable set to 8 and another to 10. In our results, we present the absolute error of the first-order functional derivative of the FTE under different conditions, showing the standard deviation over 10 runs. We also display the relative error for the BHE, highlighting the impact of including a specific loss function, which reduces the error significantly. Our main findings indicate that our model achieves relative error orders typical for PINNs, around 1,000th, even with a polynomial degree of 1,000. This demonstrates our model's ability to represent complex functions effectively, surpassing the capabilities of existing state-of-the-art algorithms. We visualize the analytic solution, our predictions, and the absolute error for a model trained on the FTE, noting that some points used for visualization were not part of the training set, showcasing our model's ability to extrapolate beyond its training data. We also illustrate the absolute error of the first-order functional derivative at specific points, again noting that these points were not included in the training set, with errors increasing at the edges of intervals due to Runge's phenomenon. Section Summary. In this section, we numerically solve the functional transport equation, FTE, and boundary heat equation, BHE, using a 4-layer physics-informed neural network, PIN, and evaluate our model's performance through absolute and relative error metrics. Our results demonstrate that our model achieves a typical relative error of approximately 10⁻³ even at high polynomial degrees, significantly improving upon existing algorithms and showcasing its ability to extrapolate beyond the training data. Section. Result. Burgers-Hoff equation. In this section, we present our main result related to the Burgers-Hoff equation. Our model achieves a relative error of about 1,000th, which is typical for physics-informed neural networks, PINNs. We assess the theoretical convergence of the cylindrical approximation in our figures and appendix. One figure shows the relative error of the first-order functional derivatives when the angle is 0. Notably, some of the points used in this figure were not part of the training dataset, demonstrating our model's ability to make predictions beyond its training data. We also find that by adding a loss term that enforces the condition that the function equals 0 at the origin, we can reduce the error by a factor of 10. Another figure illustrates the analytic solution, our model's predictions, and the absolute error for a model trained on the Burgers-Hoff equation with a degree of 20 under a specific initial condition. The absolute error related to the first coefficient is 1/10,000th of the solution scale, indicating that our model accurately learns the angle in relation to this coefficient, which is the most significant in the analytic solution. In contrast, the absolute error concerning the 19th coefficient is comparable to the solution scale, which we expect since the solution's dependence on this coefficient is much weaker than on the first coefficient. This relationship is clear from our equations, which show that higher degree terms diminish rapidly with respect to certain parameters, and the solution is primarily influenced by coefficients with values close to 1. Thus, optimizing our model for the 19th coefficient has a minimal impact on reducing the loss function. Lastly, we provide additional experimental results in the appendix, including a comparison with the carbon monophosphide ALS algorithm.